From the University of Florida, formerly from Rutgers University, one of our most accomplished and brilliant alumni from the math department, who will talk about an amazing theorem that is rational. Everything, it is 3 to 1 plus anything is always rational. Really an amazing theorem. As usual, we're going to take Vince Vatter out for dinner. If you'd like to join us, please let me know as soon as possible right after the talk. Thank you. 6:45.
Thank you for the invitation and thanks for attending. So I'm going to talk about permutation patterns. So I have to start with the basic definition of permutation containment. So throughout this talk, I'm going to think about permutations instead of, usually I think about them in list notation, just as a list of numbers. Instead, I'll probably draw them most of the time. So for instance, I might think about a permutation like this. Okay, and what I mean basically is just, here are the numbers 1, 2, 3, 4, 5, 6. I'm just reading from bottom to top. And I'm thinking about the permutation as being the list I get if I read these from left to right. So I see 3, 6, 1, 4, 5, 2. And this contains a lot of smaller permutations. For example, if I take this point, and maybe this point, and this point, now this is sort of a 2, this is a 3, and this is a 1. Right, so those look like this figure, and that's 2, 3, 1. So this permutation contains 2, 3, 1. So that's the basic definition throughout the entire talk. And like Jerome said, the goal today is to talk about 3, 2, 1 avoiding permutations. The example I drew is not 3, 2, 1 avoiding because I could take this, the 6, the 4, and the 2, and that's a copy of 3, 2, 1. Okay, but I'm going to talk about a few different classes throughout. So, I'm interested in permutation classes. These are sets of permutations of all different lengths that are closed downward in this order. Okay. So you might think about this order I've just defined as a poset on a set of all finite permutations. And then I'm interested in the downsets. But for historical reasons, we call them permutation classes. And every permutation class can be defined in terms of its basis. These are the minimal permutations not in the class. So the basis might be 1 or 2 or any number of permutations. And if we have B being a set of permutations, we'll write AB of B to be the class with basis B. Or maybe I'll just write the class of permutations avoiding B. And the other object we're interested in, if we've got a permutation class, we might want to think about its generating function. Okay, I can define that as the sum of all pi in the class, x to the length of pi. Or another way we could do it is the sum of all n the number of permutations in that class of length n, that's where we do the Sn times xn. Okay, so for a long time I've been interested in what types of generating functions we can get. And more than that, in sort of sufficient and necessary conditions to guarantee certain types of generating functions. First, I want to start with a couple negative results. The first observation I want to make is that bases can be infinite. Ooh. If you believe in infinity. So remember, the base is the minimal permutations not in the class, and I'm just claiming I can get an infinite set of minimal permutations. So really I'm claiming that there's an infinite anti-chain. Okay.
Can you put infinite quotation marks?
Okay. So there are infinite antichains. And this is actually fairly easy to see. Let me just draw you a picture of one. The lines are just to help me draw this thing. Okay, so this is the permutation, I don't know, 2, 3, 5, 1, etc. Okay, and the reason this is an infinite antichain is actually very easy to see. Let's form what I like to call the inversion graph, or what a lot of other people call the permutation graph. So I'm going to draw an edge between two elements of the permutation if they form an inversion. So let me get rid of these lines that I used to help me draw it. Okay. And now I'm going to draw in all the inversions. See what I did? I just drew an edge between two elements if they're in an inversion. And now if you stretch it apart, what you see, so we've got these two ends here. They're both adjacent to something. And then we've got a path containing 1, 2, 3, 4, 5 vertices. 1, 2, 3, 4, 5 vertices. And then we have another 2 vertices coming off. So this, we tend to call this like a call this a split end path. Now, if you just go and look at this definition of permutation containment, if a big permutation contains a smaller one, if I form the two inversion graphs, the big inversion graph is going to contain the smaller inversion graph. But if I take these split end paths of all lengths, none of them is going to be contained in any other. So none of these permutations can be contained in any other. Okay, so we have an infinite antichain of permutations. Now, if you believe in infinity, this is bad news for the generating functions. So I can let U be this antichain. It contains, the way I've defined it, I guess, it really contains one element of each odd length. Okay, but there's infinitely many, and they're all of different lengths. Now consider AV of T. Okay, for all subsets of this infinite antichain. So I'm going to avoid some subset of these things. Well, what's going to happen is we're going to get infinitely many different classes. And they've got to be different because they have different bases. And they also have to have different enumerations because all the basis elements are different lengths. So we get, I suppose you want quotes on this too. Uncountably many different generating functions. Now, as soon as we have uncountably many different generating functions, they can't all be holonomic or definite. Or if you don't know those words, just they can't all be nice.
They don't exist.
What's that?
They cannot all exist. Most of them will not exist. They're meaningless. Nonsense.
Yeah, sure.
Uncountably many, but how many?
Uh,
2 to the aleph naught, or?
Yeah. Yeah, in fact, there can't be any more than that because they're counted in many permutations, right? So we couldn't possibly get more classes. Okay, so we have a lot of classes. So if we're going to say anything in general, we need to narrow our search. So what about classes with rational generating functions? So we might hope that the classes with rational generating functions are sufficiently nice that we can characterize them. Could we characterize them? Well, another result that Tyrone isn't going to like, this is joined with Michael Albert and Robert Brignall. And right now it's on the archive. Take any permutation class you want. I can embed it in a permutation class that has a rational generating function. So I hope this result convinces you that this is still way too big a haystack to characterize, because anything I take, no matter how nasty the permutation class is, right, I can take one of these guys, but then I can enlarge it a little bit and have a rational generating function. So there's not going to be a nice characterization of these. And so there's a couple ways we can fix that. One way that we've been talking about lately is instead we'll look at the strongly rational classes. Okay, and the definition here is that C and all its subclasses are rational. So once I restrict to these strongly rational classes, there's some hope for characterization, but that's not the topic of today's talk. But there is still some hope here. Another thing you might do is instead of asking for a characterization, just ask for sufficient conditions. Or you might want to automatically compute these things. Right? Once you know that it's rational, you might want to be able to find that rational generating function. Okay, well, there's a few tools. One that I worked on when I was a graduate student. It's this theory of finitely labeled generating trees. It's implemented in a Maple package called finlabel. And it comes with some sufficient conditions for a class to be rational. And if your class meets those conditions, it'll compute that rational generating function for you. This was later generalized by Michael Albert and Nick Ruskuc and Steve Linton into something called the insertion encoding. So it was described in 2000 and let's say 2005 or 6. It wasn't implemented until I needed it for another project I was working on and wrote this Maple package called insertion encoding. In 2010. So there are two Maple packages out there. This one is strictly more powerful than finitely. So those will just give you the rational generating function. Another Maple package I should mention is the Rome's Maple package WILF, later extended to WILF Plus. Okay, so this will do automatic enumeration. This time I'm going to put it in quotes because it's not going to give you a generating function. It's not going to give you a formula. It's going to give you a polynomial time algorithm to compute the sequence. But of course, this comes with no guarantees of rationality. So this is another tool we can use.
Yeah, but that's not a drawback. Often it's more interesting. Rational means boring, so many cases it's not that much.
Okay, well, I hope to convince you in this talk that these rational generating functions are interesting.
No, they're interesting in a negative sense. Right? That's not interesting, very interesting.
Okay, not only does it come with no guarantee of rationality, there are also a lot of rational classes it can't handle. For example, 321, 2143 can't be done.
This is the only one that it cannot done, while 17 others it can do very well.
Fine, okay, but humans can do this one very easily, and your computer program can't do it.
Yeah, but 17, the other 17 is much hard for humans. Probably.
Okay. Yes, so if you avoid 321 and something else of length 4, WILF can handle 94% of them. But this is one it can't handle, and this has a rational generating function, as we'll see. Another tool which I talked about 2 years ago here, are what's called geometric grid classes. And the idea with these is that you take some matrix and you divide it up into cells. We usually think about this being drawn on the plane, so these are just unit squares. And in each unit square, I can draw a diagonal line, or I can leave it blank. So for instance, I could draw this, this. So here I'm drawing 5 diagonal lines. Okay, so this is how we think about geometric grid classes. The permutation class defined by this picture is the set of all permutations that I can draw on it in sort of that geometric sense that up in the upper left. So I might take points here, 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 and so on and so forth. Okay, as long as I take no two on a common horizontal or vertical line, I'll get a permutation. And this is known as a geometric grid class. So all permutations that can be drawn on this figure. When we started investigating these a few years ago, this was Michael Albert, Mike Atkinson, Mathilde Bouvet, Nick Ruskuc, and myself. And this is around 2010. If you take one of these geometric grid classes, so you can take any matrix you want and adding these diagonal lines, you get a rational generating function and you have a finite basis.
And is it implemented?
Not at all.
Okay.
So as Jerome said, this really needs to be implemented somehow. Our proof is non-constructive. So it doesn't necessarily suggest how to implement it in Maple. If one could implement this in Maple, well, Mike Atkinson and Michael Elbert and Robert Brignall have written a few papers where they actually just take classes that happen to be geometric grid classes, figure out what geometric grid classes they are, and then figure out how to enumerate them. So if you wrote this in Maple, your Maple package could write these papers for us. I'll say a little bit about the proof. The proof is that we convert these permutations that lie in this geometric grid class into regular languages. And then regular languages are known to have rational generating functions. Let me give you an example. Where these regular languages come from. Okay, let's say this was our matrix. So I've got 4 cells that are filled with line segments of slope 1. And I've got some permutations drawn here. And let me label the cells A, B, C, and D. Now, every permutation has, I'm going to say that every line segment is oriented from its bottom left to its upper right. And what I want to think of, I'm going to write down a word that describes this permutation. And I'm going to think of starting in the bottom left of every single cell and traversing them at the same speed. And when I hit a point, I'm going to write down the letter of the cell that point's in. So as I traverse these all together, the first point I'm going to hit is right here. That's an A. And then I'm going to keep traversing. I'm going to hit this B. And then I'm going to hit, I think, this A, or you could make a case it might be that C. And then I'll hit the C, and then I'll hit the final D up there. So given a geometric grid class, we can write down some, or a permutation in a geometric grid class, we can write down some word that describes it. Now there's a couple issues with this, using this word for enumeration. One is that these things aren't uniquely gridded, right? So I could slide this point up here and change it from an A to a C. Or another problem is, remember, when we're writing down this A or this C, we said it doesn't really matter. It could go either way. And that's because these cells don't interact. They're in different rows and different columns. So there's some partial commutativity, and then there's some regridding mess. Now, in this particular case, it's fairly easy to explain these rules. In fact, for any particular case, it's fairly easy to explain them. But when you start getting into more general rules, it gets more complicated when you're talking about how you're going to regrid things, and permutations might have many, many words that describe them.
Oh, so you can use ad hoc methods for specific examples?
Yes, that's what we do. We use ad hoc methods. But if you write down the matrix, there's no computer program that can give you the regular language. So another technique.
What do you mean by that last statement? What is the input?
If you describe this matrix,
What do you mean by that?
describe this rectangular system of cells. So you'd say, okay, this one's empty, this one's increasing, 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 empty.
Okay.
Then we don't have a computer program right now that can describe.
That does not mean that it's not.
Oh, I mean, we've proved it exists,
Oh.
right? Because we've proved this there. So we know it's a regular language. But we don't know how to effectively compute it. So we don't know how to automate this step of getting a regular language that describes, in a one-to-one manner, the permutations in that geometric grid class. So this really needs to be done by somebody. Okay. So I want to talk about another tool, and then I'll get to our result. Robert and Atkinson in 2005 wrote this really foundational paper in the field where they studied what's known as the substitution decomposition. The basic idea with the substitution decomposition is you can take a permutation, and let's say it's 2, 4, 1, 3. And you can take these points in the permutation, and maybe you can think about blowing them up by smaller permutations and getting a bigger permutation. And certain permutation classes can be described very nicely this way, where all of the permutations are inflations of very small things by smaller permutations, which are themselves inflations of small things. And when this happens to work, they always get an algebraic equation for the class. But they showed, as one of the consequences of their work, and I should state this is kind of a minor consequence of this really foundational work, but they said every finitely based, every finitely based subclass, proper subclass, of the 2, 3, 1 avoiders has a rational generating function. Okay, and this is interesting because the 2, 3, 1 avoiders by themselves have, they're counted by the Catalan numbers. So they have an algebraic generating function, a non-rational generating function. But then if you take any proper subclass, so that means you're adding at least one more restriction, you drop out of algebraic into rational. So one way to think about this might be that AV231 is barely non-rational.
But you're talking about 31.
I'm going to get to that.
Yeah, that's already known.
This is already known in 2005 that AV231 was
And
barely
then
non-rational.
anything with dick paths? Because 231 in trivial corresponding with dick paths.
It does. But then when you add other restrictions, they don't.
It's not naturally natural.
It's not natural. Yeah, well, I mean, you can think about this in terms of dick paths. It's not obvious in terms of dick paths.
So some classes of dick paths, it's not obvious. But that's not how you do it.
That's not how they do it, no. And I think if you proved the dick path version of this, it would be exactly the same proof. Okay, so they show that this thing is barely non-rational. Okay, and they made a conjecture. Oh, and I should say, I want to add this finitely based hypothesis because otherwise you might try and play around with these infinite anti-chains and create something that isn't even holonomic. Now in this case you don't need this because there is no infinite anti-chain in here. This class doesn't have one, so every proper subclass is going to be finitely based because you're going to have finitely many minimal permutations in that class. But they made this conjecture